Okay. So today we're in our last exercise, 7F, and we have a real life application of trigonometric functions. So that's going to be exciting. And what we're looking at really is we're looking at modelling with trig functions. So when we're modelling, what that means is we're using a trig function to describe some real life situation. So we'll have a read of the question. We're really going to rely on our calculator a fair bit in this exercise. So again, it's an opportunity for us to reiterate those calculator skills and make sure we have a good comprehension and conception on how to use those. So we have an entomologist, that's someone who studies insects, all right? An entomologist studying a variety of mosquitoes observes and estimates the population of the colony for 16 weeks. If T is the number of weeks after the initial estimate is made, the population can be modelled by, and we're given a function. Okay, we're given a trigonometric function. And then we're asked a series of questions about it. Okay? So when we're confronted with this kind of question, the first thing we want to do is graph it in our calculator, because then we're just going to G-solve all of the relevant questions off of it. Alright? So what we have P of T, okay, the population with regards to time. Alright? And so what that means is time is on the x-axis and the population is on the y-axis. And it's equal to 7,000 plus 2,000 sine pi t on 8. Alright, so if we think about the basic sine function, let's pull these values out first. Alright, so the amplitude of the function, right, is the coefficient of sine. So which one's going to be the amplitude? 2,000. It's the number in front of sine. Okay, it's not always the first number. Sometimes I will mix it up and swap it around a little bit. It's always the number that's in front of sine. So the amplitude is 2,000. What that means is from the principal axis, it goes up 2,000 and down 2,000. And then this d by itself, this positive 7,000, is the principal axis. That's how much it's been shifted up. All right? So our principal axis is 7,000. And then our b value is just pi on 8, right? Pi on 8, because we've got t by itself if we pull the pi on 8 out the front. All right? b is pi on 8. b is always the coefficient of the variable. Okay, so I'm just abstracting the parts of the function there. All right, let's graph it. So in your graph mode in your calculator, we're just going to type in exactly what we've got. 7,000 plus 2,000 sine, and I'm going to use heaps of brackets. We've got pi, and we use x because we don't have a variable t, but remember x and t, that's the x-axis. Pi x on top of 8. Alright, so I've typed it all in. I've got all my brackets done. I'll wait for you guys to get it in. Okay, so let's graph it, and then what we're going to do is I can't see a thing. All right, need to change my V window here. So with these problems, we only consider positive values of time. We're never looking at time going back in the past. We're always saying from time is 0 onwards. All right. So let's bring up our V window. We go Shift V window to bring it up. And so what that means, right, is if I'm graphing it, I'm only interested in this quadrant because I'm interested in positive values of time and positive values of population. We can't have a negative population. That doesn't make sense, does it? You can't have a population that's below 0. You can't have a negative amount of mosquitoes. So we're going to change this a bit. So our y min is going to be 0 and our x min is going to be 0. All right, and so what I'm saying there is we're dealing with this quadrant. All right, x min 0, y min 0 stops us going anywhere else. We're looking in this region. Next, let's think about the y max, the highest the y value can possibly be. And all it is the principal axis plus the amplitude. All right, because this is how much it's shifted up, and then this is how much it increases from the principal axis. So 7,000 plus 2,000, the highest this function can possibly go is 9,000. All right, so we're adding the a and the d value together. That's why it helps to abstract them from the function. All right, we'll just add them together, and that will always be your y max for any trig function that you graph. Okay? And then for the period, for the x max, now I'm going to talk about two ways this is done. The first is that we probably want to see one wavelength of it, okay? And remember, one wavelength, one wavelength is equal to 2 pi divided by b. Well, what is our value of b? Our value of b is pi on 8. So that means for our x max, okay, this is a foolproof way. It requires no thought whatsoever. It's just an algorithm. We just put in 2 pi divided by, and then the b value, pi on 8. Okay? And you can literally type that in where it says x max. All right, so we'll do that, and we'll process it, see what it equates to, and then we'll make a connection. So I have 2 pi divided by, and then I'm going to put my pi on 8 in brackets so that it doesn't mix anything up. Pi on 8. Okay, and if you evaluate that, 16. That's fascinating. The entomologist is studying the colony for 16 weeks. So it sort of gives us a hint there as to how long we should look at this for. 16 weeks, all right? So we're setting our x max as 16. Okay, all that's lovely. Let's graph it and look at that beautiful function, okay? So if you get the V window right, you don't have to fiddle around with it. It's just going to be straight there, and we're ready to G-solve all of the stuff straight off it. So just on our graph here, this is the population, all right? So it starts to going up, and then it starts declining, and then along here we have time in weeks, right? Time in weeks. Okay, so let's answer the questions. The first question says, find the initial estimate of the population. Because it's a model, it's an estimate. It's not describing it exactly, it's an approximation. And so initial, that means at the start. It means when time is 0. All right? And so there's basically 3 ways we can do this. All right? If we press trace, okay, F1 is trace. All right? And we can move along it, right? You can move along it using your arrows, but you can also type in any x value and it will tell you the corresponding population during that time. So for instance, if I press x is 5, all right, it's going to take me to the point where x is 5. It's taking me here, that's where my white cross is, and it's telling me the population. If I press x is 3, okay, it's going to take me to that location, all right, up here. That's where my white cross is, and here's the population. We want to know the population when the time is 0. So we're just going to type in x is 0. And we've got a population of 7,000. Unit, mosquitoes. Okay, so our initial estimate is 7,000 mosquitoes. We're just G-solving it straight off of. Okay, so that's one way using our calculator, okay, just tracing along it. What's another feature of this point? What is it? When time is 0? The D value. Hey! Yes! This happened yesterday, didn't it?
Yeah.
That's okay, we'll manage.
No.
Alright. Alright, give me a bit to compose myself here. What's that? 7,000, that's 9,000. 5,000. All right, so I'm just going to have to issue calculator instructions. I'm going to write them up. So the second way, two ways. This is the point I want to make. We've G-solved the initial estimate. What is that point on the graph?
The D value.
It's the D value, good. But what about like what's it crossing? The y-axis. So it's the y-intercept, isn't it? It's where it crosses the y-axis. So another way we can determine this value when time is 0 is G-solve, so that's F5, and y-intercept. When time is 0, the initial estimate is going to be the y-intercept. All right, so make sure you're competent with that one. Okay, so that's the second process. Let's go to the third one, G-solve. Okay, and then we're going to press the across arrow, which corresponds with F6, and this brings up a number of more functions for us to look at. And you can see we've got X calc and we've got Y calc. Okay, now what's on our X-axis? We have time. What's on our Y-axis? We have population. We are asked, what is the initial population? All right, so we are asked to do a Y calc. All right, if it helps, write that down. Y equals population, X equals time. Because the question is going to ask you both. It's going to ask you when, it's going to ask you what's the size of the population, and so that's going to dictate whether you're doing an X calc or a Y calc. All right, if we're doing a Y calc, it says enter the X value. We want to know when X is 0. So we type in X is 0, and it's going to bring up that 7,000. Okay, so they are three ways we can get it from the graph. All right, I think this way is going to be the most straightforward. All right, and so you can sort of forget the others. This way here, because that allows us to switch between both time and population. All right, when we're asked to find it. Okay, just one more connection though that I want to point out is this one here. We have, hey Kevin.
Attention all staff and students. Please note that we are currently experiencing a power outage. It is being investigated. Thank you.
Didn't notice. All right. Okay. One more connection. All right. We have this. This is our function, right? This is our function. It says find the initial estimate. That means when time is 0. So you could take that 0, right? And you're putting it where the t value is. You're going to put 0 there. Okay? And if you type this statement into your calculator in RunMath, 7,000 plus 2,000 sine pi of 0 on 8, guess what you'll get? 7,000. Okay, so like 4 ways. Let's ship on because we're taking too long with that. So the next part says, determine the estimated population after 6 weeks. All right, so it's saying, what's the population when time is 6? All right, so we're going to just go here. G-solve, we'll press the across arrow. We want to know the population when time is 6. All right, so I'll keep doing it on my computer here. So when time is 6, I've got 8414. Excellent, thank you. So that's P of 6, right? That's the population when time is 6. 8414.2, and we'll round to the nearest figure, okay? The nearest whole number, mosquitoes. Very good. Okay, excellent. Move on to C. When is the population 8,600? So if we have a look at our graph here, here's 9,000, right? That's the highest it gets. So 8,600 is like here, okay? And we're saying, what time does it reach 8,600? It's going to be this location and this location. Both of those periods of time have a population of 8,600. So when? It's asking for time. Time is an X. We're doing this. G-solve, across arrow, X calc. We want to know the time when the population is 8,600. Okay, so make sure we do that. So go G-solve, press your across arrow. We want to do an X calc. We want to know the time when the population is 8,600. Type that in, and it's going to take you to 2 locations on the graph. The first one is 2.36,
5.64.
And 5.64. 2.361.
5.638.
Thank you. I'll write them next to each other. 5.64, 2.36. Okay, and the unit, what's the time unit we're dealing with? Weeks. Okay, so at that period of time, the population is 8,600 mosquitoes. Okay. During which interval of time does the population exceed 8,000? Okay, so well, here's 8,600. We're asking for time, the interval of time, when it goes over 8,000. So pretty similar, except now we're looking at 8,000. All right, and so because I've got a pretty bad graph here, it's going to be those points again, right? It's close enough to. So we're doing the exact same thing. We want to know when. When does the population exceed 8,000? So we're doing a G-solve, press the across arrow, X-calc, and this time the population is 8,000. All right, and so we've got 1.3 recurring, and 6.6 recurring. Which is 1.33 weeks. And 6.67 weeks. Okay, now it says what interval? That means it wants us to state it as an interval. All right, so the population exceeds, let's answer it, population exceeds 8,000 when, and we're going to write it like this, 1.33 is less than or equal to t, I should just say less than, which is less than 6.67. All right, not equal to, because we're asked when does it exceed 8,000. Well, it's equal to 8,000 at 1.33, which means it's above 8,000 after 1.33 and before 6.67. All right, so we have an interval there for when the population, when it's above 8,000, when there's heaps of mosquitoes, and that's when you don't want to go visit this place because you probably get a bite. Okay, that's that. Okay, and then the last one, draw a graph. Now in this test, guys, there's going to be a couple of graphing questions. I don't want to see any of them blank, all right? We're using our calculator. It's literally copying it from the calculator onto the page. You have to get these marks. So I've already performed a sketch of it, all right? But what you'll do, when you're sketching it, you'll come up. We need to make sure we label our axes. We figured out that the wavelength was 16, okay? So we did 2 pi divided by 8, 2 pi divided by pi and 8, and we got 16, right? And so here's 16, that's one wavelength. Half of it will be 8, okay? So you've got those units there, and you can just fill in the rest just by halving it, 4, 8, 12. And then, you don't have to draw this perfectly. What we're mainly interested in is this part being to scale. And so if you haven't included this whole part here, gone up by 1,000 each time, you can just indicate that by a little squiggle there to say not proportional to. We've skipped quite a few numbers. All right. So we've got time, we've got population. Make sure you're labeling it. Make sure you've got the curve approximately right so that each position corresponds with its respective value of time. Labeling the x-axis, and that's it. Okay. Make sure you get these graphing rights. All right, so that's modeling with trig functions. So we're using our calculator a fair bit. All right, G-solve, across arrow, are we doing X, are we doing Y? Write this down, because that's going to help you. It's going to tell you whether I do an X-calc or a Y-calc. I reckon that's it. Let's get into it.